Thank you all for coming. Our speaker today is Raymond Shaw. He received his doctorate from Penn State University, and after that he joined NCAR as a postdoc in the ASP program. From there, he moved to Michigan Tech University, where he is still, except for a couple of sabbaticals to Cornell and to the Institute for Tropospheric Research in Leipzig. So I was going to mention a little bit when I first met him back in 2003 on the IDEAS program, which stands for the Instrument Development and Education in Airborne Science. It sounds like he's going to talk about that a little more detail, so I'll let him go from here. So, Raymond Shaw.
Thanks. Well, it turns green. Okay. So thanks very much for the invitation to speak. Stuart and Jeff and several people encouraged me a couple of months ago to set up an appointment to come and visit. And for me, it's a little bit like coming home. I wasn't a postdoc for very long here, but it's, a lot of familiar faces and good memories of being here. And I guess without getting sappy, it really is true that ASP is the kind of thing that makes all the difference. That level of freedom. Kind of freedom to be able to roam around and do things and work with a variety of people was very, very exciting. Wojtek, you have a question already. I'm not even past my introduction and you're already asking a question. Okay, there we go. Is that better? Okay. It does. Not just old times, but yes, regular time. Okay, let's get started. So I'm going to talk about holographic measurements of cloud mixing and cloud inhomogeneity, and I hope that will become clear as I go on. But I want to make sure that I recognize collaborators. Matt Beals and Jacob Fugel were both PhD students with me. Matt has since moved on just recently to MIT Lincoln Laboratory, where he's doing work that he can't tell me about, I guess. That's right. That's exactly right. Jacob was here, so many of you know Jacob, and now he's at Mainz University and Max Planck Institute for Chemistry, there with Stefan Bormann. And Scott Spuler and Jeff Stith, of course you know, are here, and they have been involved with this instrument that I'm going to discuss for quite a while. So this is a little bit of a different kind of talk. EOL is the one place I can come and talk about an instrument and not have to feel like I need to apologize for talking about an instrument. Most people just want to hear a couple words about the instrument and then see the science. So I'm warning you, the first part of the talk will be about this instrument that we call Holodeck. And yes, that's a little bit of a twist on Star Trek for those of you who are Star Trek fans. I'll describe it in a little more detail as we go along. But I just want to say something about the scientific goal, kind of the overarching theme of the talk here. And that is that we want to make measurements of the droplet size distribution in clouds. So there are many instruments that do this, FSSP, CDP, there are all these acronyms for different instruments. And of course, the instruments all have their strengths and weaknesses. One of the things that we wanted to avoid when we came up with the idea of building a holographic instrument was the necessity to average over long lengths to be able to build up adequate statistics to form a size distribution. So instead of having to average over many tens of meters or 100 meters, we want to be able to take one snapshot, look at a size distribution that comes from a single little, let's say fist-sized volume of air. And so I've tried to show that. In fact, I think Jeff is the one that made this cartoon that's illustrated in this cartoon. So holography, at least the way it's implemented in our instrument, it captures sequential, discrete volumes, and everything inside of the volume is imaged, and so we have the three-dimensional distribution. We can look at the spatial distribution. We can look at shapes of ice crystals. I'm going to be focusing on warm clouds here. You'll see some ice images, but I won't spend very much time discussing that. Okay, so that's the motivation. So let's talk about holography and the instrument, first of all. inline holography is the geometry of holography that we're using. And basically, as you know probably, to make a hologram, you basically have to interfere two waves. And in this case, instead of having two waves that we bring together on a sensor from different directions, we actually have one plane wave that comes in and shines on a detector. In this case, it's a CCD chip. But then each particle that is inside of the path or within the path of that plane wave emits its own little wavelet. You can think of kind of a spherical wave emitted from the particle. And so then we get an interference pattern between that spherical wave from the particle and the plane wave from the laser. And the details of this interference pattern, this ring pattern, depend on the distance between the particle and the detector. So when we get this interference pattern, we essentially get different terms. This would be a traditional diffraction term. This is just the unimpeded beam. And then these cross terms are the interference. So all of the excitement of holography is in these cross terms. And in fact, if you do this analytically for a plane wave and a sphere, a spherical particle, in the far field limit, then you basically get the initial beam, and you get diffraction. And I'm using C and Q here. It doesn't even matter what C and Q are. C and Q are basically the diffraction pattern you would get from a circular aperture. So it's a Bessel function. That's where the Airy disk comes from. This is, anybody who does optics knows about resolution limits come from Airy disk and things like that. So that's what this is. The important thing for you to recognize is that C and Q are functions that depend both upon Z, the distance of the particle from the detector, and the diameter of the particle. And these two pieces of information are tied up with each other, and you can't separate them. So the diameter of the particle and the distance of the particle to the detector. But in the interference term, we have C and Q, but also this sign of a phase factor. And the phase factor, it turns out, only depends on Z. R, in this case, is the radial coordinate. It's not the radius of the particle. So this phase factor does not depend on the diameter of the particle. It only depends on the position of the particle along the optical axis of the system. So the hologram has encoded in it this ring structure. You can think of this as a Bessel function diffraction pattern that is modulated by this high-frequency ring pattern. And the high frequencies tell you about the three-dimensional position of the particle. So encoded in this pattern is all of the information about the size and the three-dimensional position of the particle. That's what makes it an exciting method to use. Okay, so because of that, we can take an interference pattern that might just look like a lot of noise, and then instead of using analytical theory, we can actually we can do this on a computer. We can record this on a CCD. That's the image. And we can convolve that image with a propagation kernel, the details of which don't really matter for right now. But this is known in, take a class or read a book in Fourier optics, and you can get this. And then that gives you the image at a farther distance, in this case, distance Z, away from the detector plane. And lo and behold, here are two cloud droplets that have been reconstructed digitally inside of a computer. And I should point out, I guess, in all fairness, that we're not the first people to try to do holographic measurements in the atmosphere. But most of the prior attempts were based on photographic emulsions. In fact, Wojtek, I think you told me once that convinced you to stop being an experimentalist.
Yes, exactly.
So
because I spent time playing with pieces of glass in a dark room, because doing shifting laser, and oh boy, I said I don't want to do it for my life. So
yeah.
I
Well,
switched to modeling.
this has just about convinced me to stop being an experimentalist too. Not quite, but so yeah. Instead of doing that in a dark room now, it's done in a computer, and we can do that propagation inside of the computer. It makes it much easier to automate the process. Um, so in practice, what we do is we take Fourier transforms of all of these fields, and there we go, yeah. And we basically Fourier transform, then multiply by this kernel function, then inverse Fourier transform, and graphical processing units are great and efficient tools for doing all of these FFTs. So we've been able to really speed that process up and implement everything in CUDA on these GPU clusters. So that's sort of made this a reality for us. So let's see, I want to show you a movie so you see what it looks like. So this is a hologram of a very large ice crystal. So this is what it looks like at the plane of the detector. You can maybe just make out the sort of a very rough, fuzzy shape of an ice crystal. So now what I'm doing is, you can see this is the distance. I'm slicing, I'm propagating along the optical axis with this kernel function. I'm moving along and eventually I'll actually hit the depth at which the particle was really located, and you'll see it come in almost magically, come into focus. And you can see a lot of details on the, of the crystals. So all of this detailed information is encoded in that ring structure on the CCD, captured by the CCD. And then it just becomes our challenge to come up with algorithms. So propagating is a known thing, a solved problem, but then you have to extract this information from the image, and that's an kind of a non-trivial problem to get rid of noise, to find particles, get their statistics, and all of these kinds of things. Yes.
This is a pulse system.
It is, yeah. That's exactly right. So we use a pulse laser, and that's essentially making a little flashed image of whatever set of droplets are in the beam of the instrument. That might become a little clearer. I'll show the instrument in a little more detail here. So here's Holodeck history, and I'm only taking you through this. Most audiences, I think, wouldn't be interested. But I think one of the nice stories here that Jeff and I have talked about multiple times is Holodeck is I think a nice example of a collaboration between a university and NCAR and EOL in particular, where we've been able to do much more, I think, than at least we at a university would have been able to do by ourselves. And so I think you'll be able to see how it's, believe it or not, more than 10 years now that we've been working on this. So I remember in early 2003 talking to Jeff Stith on the phone, and he was twisting my arm to asking us if we had something we wanted to fly, because there was this project called Ideas, and it was a perfect opportunity to fly an instrument and sort of shake things down and test something new and crazy. And we had been developing holography in the laboratory for particle turbulence measurements. And so if I would have known then what I know now, I would have said no, Jeff. I would have hung up right then. But I naively thought, well, we know how to do it in the laboratory, so this should be easy. Let's just throw together kind of an instrument. So we built this thing in sort of record time, 6 months. We put it on the C-130 and flew it in Ideas 3 in fall 2003. And yeah, Don, you can see that there's a laser that goes through. We based it on FSSP kind of geometry. So any particles flying through here get imaged when that flash goes off. Okay. So then we flew the instrument. Then we had to learn how to deal with the data, and that took a long time. So we had to develop reconstruction methods that would work within the range of atmospherically relevant parameters, and learned how to deal with automated reconstruction and retrieval of complicated shapes where there aren't analytical solutions to, like spheres. So that took some time. And all of these have been, I have papers down on the bottom here. All of these have sort of been long processes. We made detailed comparisons. with other microphysical instruments on Ideas 3 to kind of prove to ourselves that the instrument worked. Then Jacob finished up and became an ASP postdoc sometime in maybe 2010 or 2009, I'm not sure, and worked with Scott Spuler to lead the development of the second version of Holodeck, which was built here at NCAR, with a very impressive lens system and that's been reported in the literature, the specifications of that and the resolution and so forth. And then since that time, Holodeck has participated in three Ideas projects, 2011, 2012, and 2013, on three different aircraft, including the C-130 and the G5 from NCAR. So there's a lot of work in these bullet points that I haven't gone through, but needless to say, it's been a 10-year process to get to this point where we can really have scientifically useful data, and it's been a collaboration in the true and sort of best sense of the word. So let's talk a little more about that. Some things that were not given bullet points, but I want to emphasize here because I want you to believe the diameters and the number densities when I show them to you later in the scientific part. We could just look the other way and take the numbers for what they are, but we've really, really pushed hard to try to develop methods to make this technique extremely robust. So some of the things that we've done, just as a little bit of an overview, when you reconstruct digitally rather than in analog, you have both amplitude and phase. And one of the things we learned along the way, maybe it would have been obvious to radar people, but to us it was sort of a discovery, was that the phase profile gives us really powerful information. When we reconstruct, here's the distance along the optical axis. This is one droplet, and real data, by the way. So this is a real cloud droplet. So there's the cloud droplet. As you reconstruct, it kind of comes into focus and then disappears. But phase gives you a very sharp, sudden flip at the position of the particle. Phase starts going down, and then all of a sudden it flips to positive. And you can talk about theoretically why that is. I don't want to go into that now, but it turns out that using phase information in addition to amplitude allows us to really have a much more robust detection of droplets and rejection of noise. Other things that we learned, we were interested, especially for our laboratory work, in knowing the three-dimensional position of particles really, really well, because we actually track them. In the lab, you can track particles through Lagrangian tracking you can't do from aircraft. So holography is limited in its depth resolution. It's sort of like us with eyes really, really close spaced. It doesn't have very good depth perception. And so the lateral resolution of holography is much better than the depth resolution. And that's bad if you want to know a three-dimensional position of a particle. So what we learned is that we could go from a depth that depended on d squared, the diameter squared, to a depth that depends on essentially the pixel size squared by doing a trick. And I just want to show you this trick because it ends up being important for more than depth resolution. So basically we built a filter. And this is kind of like a matched filter. So those of you who have worked with radar or maybe with image processing, you can build a matched filter. So for example, if I want to do text recognition, if I have an image of a sheet of text and I want to find all the letter A's, I can basically take a letter A, take a Fourier transform, and build a filter out of that Fourier transformed A, and then I can convolve it with the image, and I get little bright spots everywhere there's a letter A, okay? And you can make that size dependent or not, depending on how you do it. So we're able to get, here's Z depth now, instead of the normal way of doing things, if we filter, if we know the diameter of the particle, okay, if we know the diameter of the particle, we can build a filter that is exactly built for that sized particle, and we can get this very, very sharp peak in depth. That's the peak sort of in a two-dimensional view. Okay, So that was in 2005. And we were excited, and it helped us in the laboratory. But it took us, basically, a few years, six years, I think, until we figured out that we could use this. Um, if, so the idea was, okay, this only works if you know the particle size, right? Which is unfortunate if you're in the atmosphere. You don't have the particle size. But then we thought, well, what if we just tried a range of filters and looked for the one that gives the sharpest peak? Yeah, then we would have a way of essentially finding the particle size with really, really high resolution. The way we used to find particle size, still do when we're doing things roughly, is just by counting pixels. You reconstruct an image, you say, aha, there's a dot, that's a particle, let's see how many pixels are lit up. And it gives a lot of uncertainty. It's essentially related to pixel size. But if we take a profile of intensity along the reconstruction axis, this is along the optical axis of the instrument, and then we say, well, let's filter with something equal to the drop size, and we get this very sharp peak, and I've normalized so that that's equal to 1. Then if I take a filter, if I purposely choose a filter that's the wrong size, it's the wrong droplet diameter, this is 90% of the drop size. Now the peak drops. This is 10% greater than the drop size. And again, the peak drops. And it's monotonic. So these are actually real measurements. This is not just from a computer. This is going into a laboratory and measuring, as a function of measuring real droplets and then applying this filter. And we knew what the particle size was in this case. It was 56 microns. And so you get this kind of monotonic profile if you use different filter sizes. And it allows you to determine exactly or with much higher precision, what the size of the particle was. So here's an example of a measurement that we did in the lab. So the blue histogram is particle diameter that we determined from pixel counting. And the red histogram is particle diameter that we determined from this inverse filtering approach, basically a matched filtering approach. So again, I'm showing you this because particle size ends up being very, very important for what we're going to do next, what we want to do microphysically. And having this ability to go to higher resolution really allows us to be able to push that farther and to have more confidence in our results.
But is it a given that your maximum on your filter layer is actually the best determination of the particle size?
It's not a given, but it would be theoretically expected, and it works. And we tested it in the laboratory with spherical particles of known little glass beads that are calibrated. So I would be very surprised to learn of a set of circumstances where that wasn't true. But there could be some circumstances. Yeah, Jeff.
I was just going to ask.
Oh, sorry. Two questions here.
In the field or in the presence of noise, would that maximum get blurred out? So it might not be as sharp as what you're showing right here, which is in the lab.
Yeah, well, first of all, in the lab, there is noise. These were particles. There's always more in the field, that's for sure. And sure enough, and also, if you're a careful reviewer, you'll notice that we use relatively large particles to do the lab test, and everything gets more challenging when you go down to 15 or 10 micrometers, because you're getting closer to the wavelength of light. And this inverse filter method is fundamentally dependent on the wavelength. And that's, I should have pointed that out too, that with thresholding, you never know if you're getting the absolute value right, you might have a certain precision, but it's hard to know if you're getting, what your accuracy is. But this is dependent, when you do this filtering method, then you're really tied to the wavelength. And so if you know the wavelength of your laser, then you know the diameter of the droplet. So it's much more, not just more precise, but more accurate. And the answer is yes, it gets more difficult when there's real noise. And we're still sort of dealing with how to automate that. Right now, there's a distinct human component to the data processing that's painful. Um, but yeah, so it does get more difficult. Okay, so now to some science. I think we're okay. We're about halfway through. If Stuart, where are you? 4:30, right? Okay. Okay. So to pose a scientific question now, for which we've used Holodeck, uh, I just want to ask a couple of really simple kinds of questions, and to start that, maybe to provide some interesting background. Here's something that most of you are probably used to seeing, these kinds of profiles through clouds. This is liquid water content flying through a cumulus cloud in Barbados, or off of the island of Barbados. And this was with the Octos system from Germany, my collaborator Holger Siebert. And here's energy dissipation rate that we can measure, and the liquid water potential temperature. And what you can see is that if you start looking at temperature, vertical velocity, and buoyancy especially, at the edges of clouds, where the liquid water content isn't zero necessarily, but close to zero, there are very strong signatures of what has come to be known as subsiding shells in clouds. So there's a distinct region around the cloud that is influenced by the mixing process. And the older the cloud is in terms of its lifetime, the more pronounced this kind of environmental halo or subsiding shell becomes. And so this is, I think, part of the entrainment and mixing process that will come into this story a little bit later on. So I just wanted to bring that to your attention. I think many of you, even in this audience, have done work related to these kinds of shells. Okay, and here you can see it in a little more detail, but I probably don't want to spend too much time. We just looked at 3 different lifetime stages for these clouds, and as they're either actively growing or dissolving and decaying, you get different. These are convective. These are all small cumulus clouds. Yeah. Non-precipitating. That's correct. Yeah. Yeah. Maybe just the initial formation of some drizzle. Okay, so now the simple question that I want to ask. Liquid water content, which on this slide I've called capital W, is decreased when entrainment occurs, right? When we bring in dry air from the environment and reduce the liquid water content. The question is, how is that dilution manifested in terms of number density or the diameter of the particle? So this is, maybe for the rest of the talk, this is the most important equation to keep in your mind, is that there are different ways to reduce the liquid water content of a cloud. You can reduce it by reducing the number density or the diameter or some combination of the two. And this is from Ideas 2011, I think. And it just shows one example of liquid water content sort of varying in a sort of uniform way, finding values all between 0 and its maximum. But the diameter, perhaps surprisingly, almost looking binary, right? There's some variability in the diameter, but it's almost varying between 0 and its maximum value. And this is something that was, so I've pointed that out here. Droplet diameter is very different, sudden jumps between 0 and close to the maximum value.
So if you have a droplet distribution, what is the diameter? Mean diameter, mean volume diameter?
Yes, this is what we've calculated here is a mean diameter, but you can look at a mean volume diameter and the view doesn't change a whole lot.
That droplets on one side of your spectrum are going away, that your mean still stays the same, but then you change the characteristic.
That's the question. The question is what's going on, and can we probe into a little more detail? How is the droplet size distribution responding to this mixing? Yes.
Liquid water content, then V is kind of mean volume diameter.
This is mean volume. What we've plotted here is mean diameter. Yeah, we plotted mean diameter, but yep, absolutely. Um, so this is a question that was asked a long time ago by Marcia Baker and some colleagues who I think are here. One or two are here in the room, I think. Um, what happens when and this was sort of, I think, first pushed by Marcia Baker and John Latham, this concept of homogeneous versus inhomogeneous mixing, and it really boils down to understanding how how are changes in W manifested in terms of variability in number density and droplet diameter. So one way that we can do that, and something, not exactly these coordinates, but something like these coordinates were, I think, first published in this paper. That's why I'm highlighting it here. So what I've done here is plotted diameter cubed, normalized by a maximum diameter, just so that we can compare different clouds with each other. And then number density of droplets normalized by some maximum droplet number density. And if we say that, okay, let's consider thermodynamic equilibrium states for a continuous range of dilution levels. So let's go from an undiluted cloud and look at reducing the number density across a range of values here. And if we conserve mass and energy, assuming that everything is allowed to evaporate homogeneously under uniform conditions, then we can come up with a curve here. Okay, and that curve, if we know the external properties outside of the cloud and inside of the cloud, we can predict this homogeneous mixing curve. Okay, cloud dilution, cloud droplet evaporation. Okay, so this is what I will refer to as a mixing diagram for the rest of the talk. But it turns out that there are other ways. You can also conserve mass and energy, but allow the mixing as Latham and Baker sort of envisioned it first. You can allow the mixing to propagate in sort of fingers, right, where the edges of regions of cloud would evaporate completely, and then there would be regions of cloud that are left essentially untouched by the mixing. Okay, and that would look like this, presumably, where the mean diameter would remain essentially constant, but the number density would be reduced. Okay, so again, this is important for the rest of the talk. This is inhomogeneous mixing, and this is homogeneous mixing. And you can quantify this as a Domkohler number. You can basically think about speed at which the fluid mixes by turbulence compared to a phase relaxation or perhaps an evaporation timescale. So this is what we will investigate. So let me show, before we get there, I want to emphasize now, I'm going to drag you through a little bit of text this is from Baker and coworkers in 1984. I want to convince you that this is a non-trivial measurement to make, to be able to say, if I see points scattered along a line on this plot, can I really interpret what's going on with those points? So let's say I take an instrument that averages over a long distance in order to build up a size distribution, like any of the single particle counting instruments. What are the dangers that could arise? Can we fool ourselves? And it turns out that there is, as was recognized early on, there's a fundamental ambiguity. So there are filaments in this whole range of scales, from the large eddy to the Kolmogorov scale. A measuring instrument with resolution large compared to the Kolmogorov scale, so a measuring instrument that has to average over a long spatial scale, will see an average spectrum in the mixing region of the same shape as that in the original cloudy air, but simply diluted by unresolved filaments of cloud-free air. Okay, so that's the idea, is that if I have pockets of cloud air and pockets of diluted air, number density will reflect the dilution, but mean diameter is going to be completely dominated by the statistics of the undiluted regions. Okay, that's the point that they're making here. They say it again in sort of a different way. These small-scale structures would not be revealed by any standard particle measuring system, such as those in general use in cloud physics experiments. Thus, whether or not the clear air is saturated, the droplet spectrum measured by typical devices during the first part of the mixing process may be very similar to that in the adjacent high liquid water content regions. The number of droplets, however, will be diminished in the ratio of cloudy to total air averaged over by the measuring apparatus. So this is the ambiguity recognized a long time ago that has essentially been with us in, I think it's fair to say, in every study, including some of my own, every study of homogeneous, inhomogeneous mixing that we've tried to do from airborne platforms. So this is just a very rough cartoon illustrating the idea. If I have regions of cloud where all the drops are the same size, there's some mean volume diameter, and then there are regions of clouds perhaps where homogeneous mixing has occurred. Okay, so the droplets are diluted and also smaller in size. But if I now average over this with a single droplet counter, the number density will reflect that dilution, right? But the statistics of the size distribution are going to be dominated by these pockets of high liquid water content. So that will give me a signature that looks like inhomogeneous mixing. It will look like number density is going down, but mean volume diameter is staying constant. Okay, but we won't know for sure whether that's something that we can really rely on. Paluk and Baumgartner illustrated it this way, and they were some of. I think it's fair to say that one of the things that really pushed forward fast FSSPs and things like that, for example, even by Jean-Louis and Brenier, was this problem, wanting to be able to squeeze out more resolution. What's going on at these very, very high resolution scales? So the solid line here is the average concentration, the local concentration and the average concentration with distance. And I see I've managed to block the lower one with my text here. But basically the dashed and the solid lines disagree with each other in this box that has filaments. And they, in this paper in 1989, they started to get some indications of whether you could look for sort of the instrument equivalent of subgrid scale resolution. Okay, one more bit of text, because it says it just a slightly different way. This is Bernet and Brenier in 2007. So as in any single particle counter, this is after a beautiful study of homogeneous and inhomogeneous mixing from the RICO study, they acknowledge that there's this sort of fundamental ambiguity still in the results. Droplet counts in the fast FSSP must be accumulated over a specified sampling period until there are enough particles for building a statistically significant droplet size distribution. The shortest statistically significant sample length typically ranges from 10 to 100 meters. The two physical parameters that are selected here for exploring the entrainment mixing process are in fact sensitive to the heterogeneity of the droplet spatial distribution in the measured sample. Assume, for example, that a sample is made of half pure cloudy air, so that's Na and dVA. dV cubed is the mean volume diameter, and A would be adiabatic, okay? Intertwined with half diluted air, characterized by reduced value of Nd and a reduced mean volume diameter. Measurements of such a sample will exhibit a concentration, which is a 50-50 mix of the two regions, which is about equal to 0.5 Na, and a mean volume diameter, which is a 50-50 mix, but that's going to be approximately equal to dVA cubed, the undiluted diameter, okay? So one reflects the mixing and the other does not. In situ measurements with a particle counter therefore tend to disguise the lowest mean volume diameter values in a spatially heterogeneous sample, when the length scale of the heterogeneities is smaller than the resolution scale of the instrument. So that's the challenge. That's where we've come at this study with Holodeck, is with this kind of uncertainty in mind. So let's see, this is maybe just to remind you of these plots that we're going to be using of radius or diameter cubed versus number density, and the homogeneous or inhomogeneous mixing. Okay? So let me show you some data now. This is from Ideas 2011, and this was taken, data taken from the C-130, and right here over, I think, northeastern, this was RFO5, it was northeastern Colorado, I think, or maybe just southeastern Wyoming. So we targeted, the pilots sort of masterfully targeted this cloud and passed through it at 3 different levels, the top, middle, and bottom. And I can give you something where you can see all the details. I'm just going to take you through pass number 2 here, so that you can see one example of the kind of response that we get. So here's the flight track. There's pass 1, pass 2, and pass 3, decreasing in altitude. And these were small droplets. It was the cloud was just slightly supercooled. And here's pass 2 to give you an overview of what we're seeing. Here's the liquid water content. Is the black curve, and the red curve is the number density from the CDP. So you can kind of see the structure of the cloud. This is a size distribution as a function of time, with a colors representing size and the black curve representing the mean droplet diameter. So you can already see a hint that the diameter is fairly constant, even with liquid water content varying. The details don't matter here so much, but I just want to emphasize that this was an important part of the project. An important part of the measurement was the ability to measure water vapor mixing ratio and to be able to calculate things like the liquid water potential temperature, so that we could essentially get a direct measure of environmental conditions, how dry was the environment, so that we can make these homogeneous mixing lines when we assume a mixed parcel. And we also used quantities like theta L, methane, and ozone to get a measure of the dilution fraction, because these values are a little bit different inside the cloud than outside the cloud. So we have more than just the number density for estimating the fraction of entrainment. Okay. The other thing that we did in this study was to look at the turbulence from the C-130. So we looked at the second order structure functions. You can see this plateau, which allows you to get an energy dissipation rate for the cloud. And that allows us to look at essentially a transition length. This is the length scale where we would expect a transition from inhomogeneous mixing at large scales to more homogeneous mixing at small scales. And you can see that depending on how this is calculated, it's ranging from maybe 10 centimeters up to 60 or 80 centimeters. So somewhere around this length scale, we should theoretically see a transition from very inhomogeneous type of mixing down to something more smooth and homogenized in the response. At least that's the thought. That's the theory. So here's what we're able to do with Holodeck. We're able to essentially image a little region of cloud of about 15 cubic centimeters. And so this is, each of these blue dots is one cloud droplet. And we've colored them with 2 different colors here, just so that you can see just a few droplets that are the largest of the batch. Okay? And this is an undiluted hologram. Okay? Here's an example of what a hologram looks like when there has been some dilution, where the number density is decreased, the ozone mixing ratios, and water vapor, theta L, and things like that signify that there has been some dilution of this parcel. And you can see that in this case, this would be something like what you might consider homogeneous mixing, or something that has been able to mix thoroughly. So it's still spatially very, very homogeneous, and the droplet population has been suppressed. Okay, but the mean diameter is not so different from what it was. Here's the kind of measurement that first started to get us very excited about this study, was the ability to actually capture holograms where we can see mixing in the process of occurring, where we're seeing the sort of filamentary structure of cloudy and clear air propagating all the way down to this centimeter scale, where Latham and Baker and others first sort of a long time ago hypothesized that it should exist. Yeah.
So each was one shot?
Each of these is a single snapshot. So this just happened to be right at the edge of a cloud. And there's no intelligence in where the snapshots occur. That the camera is just, and the laser are just firing at some steady rate. So it's just luck. It's 3.3 hertz. So there, you get one hologram and then whatever 33 meters, and then another hologram. So it's very sparse. So it's really important in interpreting the measurements to have something like a CDP that gives you more continuous coverage. The limit is how fast you can stream data to a computer. And so it's a combination of, you can go to higher frame rates, but then you would have a smaller number of pixels per image. So it's really, at some level, it's a question of money. If you buy a faster camera and a faster computer, you can go faster.
But 10,000 frames per second, but not for long.
That's exactly right. So you can get 10,000 frames per second, but you would fill up a buffer. So you would measure, you'd have to trigger on a cloud, right? You could measure almost continuous coverage in a cloud, and then you'd have to fly for 10 or 20 minutes while you saved it all to disk. So yeah, that's what we do in the lab for our Lagrangian tracking. We have particles and a turbulence chamber, and we have high-speed cameras with onboard buffers, and we measure for 10 or 20 seconds, and then we sit there for 10 minutes and dump the data to a disk. In a lab, it's no problem, but yeah.
So when you're graphing, you have like millimeters, 8 by 140.
Yeah.
Significant.
That's the sample volume, and it can be adjusted. I mean, it depends on where you cut it off in terms of your processing. Because the laser profile gets a little weaker on the edge, so there's some nitty-gritty details that are not being shown here. There's still a little bit of art to the science, I would say, in terms of exactly how you crop that volume. I'll just point out here, though, that this is a really sort of astounding measurement to us, not just to see the 3D structure, but also to see that we've reduced the droplet number density strongly by 80% maybe for most of the distribution. And yet if you look at the large droplet bin, it's maybe only reduced by a factor of 2. So something in the mixing is not treating large droplets in the same way as it's treating small droplets, and that's really kind of an interesting thing. Yeah.
What's the difference between the shaded and the unshaded in that lower range?
Sorry. So black is the initial size distribution. It's something taken from an undiluted hologram, and so just comparing. We can't know if that's really what this hologram had before it was diluted, but it's something from nearby in the cloud pass for reference. Yeah, thanks.
Those earlier about noise also, but like in the cloud, is there any saturation type of point that you get at too many droplets or too high a concentration?
So we don't have that in the atmosphere. That almost never occurs. But if I wanted to build, one simple way to say, I want a bigger sample volume, I'll just make Holodeck's arms wider apart so that the laser goes across a wider range. But at some level, you would reach holography. Inline holography fundamentally depends on the plane wave being undisturbed. In other words, enough of the plane wave has to make it through the cloud that it still sort of looks like a plane wave, by the time it gets to the detector. And if you have a long path in cloud, then you would degrade that signal. But with Holodeck, that never happens for realistic atmospheric conditions. Yeah.
Do you have any bias due to the fact that you have the transient measurements and you have a finite volume and the big particles and the small particles don't have the same speed? So you're actually biasing relatively to what you see?
That's a really good question, but I think the answer is no, because the speed of the aircraft is so high compared to any droplet speeds. Yeah. So that you're right. For example, phase Doppler measurements in turbulence in a wind tunnel, that's something that you have to account for, is that bias for droplet size. But in this kind of situation, that's, I think, fair to say, totally negligible. Yeah, that's one of our limitations right now. In fact, it made this study difficult because these droplets are relatively small. So we have a 3 or 3.5 micron lower size limit on paper. In reality, it's probably, we all feel more comfortable with 5. So yeah, that, and you know, if I could do anything I wanted with the instrument in the future, that's one of the things I would change, is reduce its, increase its resolution a little bit, reduce that size. It depends on pixel sizes and the optical system. Scott's optical system is so well designed, we could reduce the pixel size by a factor of 2 or 3 and still, we still wouldn't be limited by the lenses. So, okay. Just a couple more slides here. I think the next one is the real punchline. So if we take all of these holograms through this pass 2 that I was showing you, and we calculate a mean volume diameter for each hologram. So each hologram contains, many hundreds of droplets. And so I take each of those droplets, that population of droplets from one hologram. I calculate the mean diameter. I calculate a number density for that hologram, and I plot it in this coordinate system, right? So here's number density and d cubed, normalized by some maximum values. And then the dashed line is the energy and mass conservation curve that I mentioned at the beginning for assuming homogeneous mixing, assuming that all the evaporation occurs in a spatially uniform environment. And this signature is extremely, I would say, favors inhomogeneous mixing in sort of a very extreme sense, and was really very surprising to us. And only when we went back and reprocessed all of our data using the new inverse filter method were we really willing to believe that this was not just an artifact of our measurement method. So for example, if you're setting thresholds, you can, depending on how you set the thresholds, it can be a function of the number density. And so you can really fool yourself. You can really fool yourself in this kind of business. And so it was very important to develop these methods so that we could get independent, sort of wavelength, sort of tracing the diameter back to a very fundamental quantity. So just one more quick example. I won't take you through all the details for this. This is from Ideas 2012. So many thanks to the University of Wyoming King Air people who helped with that project. Similar kinds of conditions, larger droplets, but there were some reasons we wanted to make sure we could do this on 2 different aircraft, because there were maybe some indications that some people have brought up questions about whether the props from the C-130 could be causing these inhomogeneous samples. And so we just wanted to be sure, measuring different aircraft, different location, and the answer is we still see the same kind of thing. Sorry, this curve is only a couple days old, so it hasn't been really polished yet. But the one thing that is interesting here is that the signal in this case isn't quite as desperately inhomogeneous as the last one. There's a hint that the sizes are falling off at high dilution fractions, and that may be a response of this kind of subsiding shell that I was discussing before. Same instrument. Everything's the same. Method for processing is the same. The only thing different is the aircraft and the cloud. Okay, I can just show you this. If you, I won't take you through the details, but if you imagine that you have a shell of preconditioned air that's subsiding from above in the cloud, then you can draw multiple lines. You can imagine homogeneous mixing curves that are from a more humid environment, and so you can find humidified environments that actually seem to fit the data points in a sort of reasonable way. So that's one of the things that we're working on now, is trying to understand that in more detail. I think I'm going to go straight to the summary. So the main message, I guess, of the talk is that this probably isn't a message that needs to be convinced here, but droplet size distributions really do matter. If you're interested in optical properties or precipitation development in clouds, you would like to know more than just the mass of the condensed phase. You would like to know something about droplet sizes and number densities. The nature of mixing is very likely scale dependent. So homogeneous and inhomogeneous mixing can be occurring simultaneously. We've seen both examples in the holograms that I've shown. Holographic measurements allow statistically robust estimates of the droplet size distribution to be measured in microphysically local volumes without the need for large-scale spatial averaging. And I think we're comfortable with making this statement now, that local size distributions from Holodeck provide really strong evidence that inhomogeneous mixing really is occurring down to the centimeter scale. So I'll end with that and take questions.
Just before we get started, or before we get into the questions, I just want to mention, I forgot to at the beginning, that this is a joint seminar with the Cloud Physics Across Scales group. So if our distribution of faces is a little bit different than we're used to, that's why. So if you can use the mic on the questions, I know we don't need it here to hear, but in order for it to be recorded. So if you can use it, okay?
Kind of two questions or comments. Yeah, is it loud enough? Okay. First is, can you kind of reproduce the mixing condition in the lab? Because when you have the lab set up, you can probably set up the inhomogeneous or homogeneous mixing kind of a state in the laboratory, and you can actually use your instrument to reproduce those curves and make sure that can be happen, and then go into the field and interpret your data accordingly later. And the second is because after you show all the data that you kind of drew the conclusion that inhomogeneous mixing is more common in the cloud edge or in the situation. Do you have any theoretical explanation to that, or sort of the real science behind that phenomena? Because I think when you have a population of droplets, large and smalls evaporate and actually help sustain the large droplet. So it's more, in my opinion, when you have that population, have large and small droplets, it's more behave like inhomogeneous mixing kind of behaviors. So it's my thought, but
so
you probably can come up with others answers.
For the first question, I would say yes, in principle, it can be done in the laboratory. It's not really an easy kind of laboratory experiment to set up. So we have a cloud chamber that we're trying to move in that direction, where we can make something related to that. Some related measurements, but it will probably be, I would have never guessed that it would take 10 years to get this, so I don't want to guess how many years it will take to get the cloud chamber ready.
Anywhere else has a similar setup, can you bring your instrument to the other lab to do the same?
It's possible. So question 2 about whether there's a possible theoretical explanation. So yeah, definitely. I mean, Baker and Latham and colleagues and many people since then have talked about many different aspects of this problem and why it may favor one or the other. Some of the first really detailed computational experiments or simulations were done by Wojtek and Andrejchuk, in showing the conditions under which one might tend to favor one type of mixing versus the other. So I should be careful. I definitely don't want to give the impression that this is a universal phenomenon. I mean, these are two clouds, both continental in reasonably dry environments. And so they're, if we went to Barbados or something like that, we might see some different things. Really, for this seminar, I was focusing more on the tool and the instrument and some of the exciting science. I can give another talk telling my opinions about why homogeneous and inhomogeneous should be favored or not under different conditions. But
can I just take an argument with your last point there?
Yes, please.
And if you can go a couple of slides back to where you showed your two very beautiful boxes with this one here, yeah. So you started your talk by saying that an instrument will average over cloudy and clear air. And I would argue that in your last slide here, you are still beyond the Kolmogorov scale. You don't have a uniformly mixed cloud, and therefore, in this particular case, you probably still have entrained air and cloudy air in the things here. And I think that will lead you to believe that this is inhomogeneous mixing, whereas it in fact is still mixing that hasn't been completed.
That's exactly true. That this I would interpret this more as so this level of dilution versus this are probably less a difference between homogeneous and inhomogeneous and more an example of whether the cascade has been allowed to run its course or not. But I can tell you that these kinds of volumes are much, much more common in the diluted regions of the cloud. And the signal both from this and from this are both inhomogeneous looking in the sense that the droplet diameter has not strongly responded to the mixing. So I think that it's, I understand the point you're making, but I think it's still, it holds in spite of that.
So Raymond, if let's leave mixing for a moment. In Poland, when they started using holography in this lab, very painful, they really wanted to look how droplets are actually spatially distributed in the cloud, and that's how we actually started. Because you remember this preferential concentration discussions, 15 years ago or so, and I would think that that's another very interesting and hopefully fruitful application of this instrument. And I'm curious whether, I'm pretty sure you look into this already, but that's a different subject than what we discuss here. Can you kind of shed some light on that? Because remember, we started with kind of the opposite end. I was saying, well, we don't see a preferential concentration. At least Jean-Louis doesn't see it. I was kind of a whatever, agitator, if you like,
pushing
people to look into this. And you were saying, no, there is. And then can you comment on that?
Yeah, it's funny because I would love to say that this is the problem that motivated me to build Holodeck, and that really wouldn't be true. Probably the main motivation was spatial distributions. And we definitely have used holography to look at spatial distributions in the laboratory. And I guess I would say that, so we could do it in clouds, and I actually pushed my graduate student to do it before he left, but the reality is it didn't happen. It hasn't really been done carefully in clouds. But part of the reason it sort of fell down a couple of notches in priority is because what we've done in the lab is so clean, and we really know the dissipation rates, and we know the droplet size, and we can control everything. And so there's no reason really to necessarily, unless you believe there's a genie in the clouds that's not in the lab. But I mean, all the physical conditions and the dimensionless parameters have been matched, including even settling parameter. And we get pretty good agreement with the DNS from Liang Ping and Lance Collins and other people. So, yeah.
Raymond, this is really exciting, and I can see there's a little bit of a difficulty here in resolution of the diameter. And I'm wondering whether that is somehow also...
You mean because of the... this bin sizing?
Yes, bin sizing in the diameter.
So that's not inherent. That bin sizing is something we chose for
the purpose
displaying
of
these results.
Okay.
I mean,
So there's
it
no
essentially depends on how many particles you have and the pixel size.
Okay.
There's essentially like a 2.5 micron.
So the diameter issue is more a lower limit as opposed to a resolution. My point was simply that I wondered whether a coarse diameter bin might at some point start biasing things to an inhomogeneous line.
Especially that there was a third cube. You know, the cube
Yeah.
power there
Yeah.
is also kind of makes things.
There are two things that bias it. So one of them is that if you turn your lower size limit into a d cubed, that becomes a horizontal line on this plot. And so if that horizontal line is right here, then we're just seeing inhomogeneous mixing because we're only looking at the drops that lie above that line.
Right.
And so of course we've checked that. And it turns out that this case, it's a little bit uncomfortably close. It's not bad in this case. It's very comfortably above that line. So that's one thing. And then of course if you have a bin width, if you have some fundamental bin size resolution, then that would hurt. But with this inverse filter approach, that goes away. We're no longer limited by pixel, if that makes sense.
Yeah. Okay. I feel more comfortable with
the
that.
lower limit is really the thing that makes you squirm a little bit.
Okay. And just the second part to this, and this goes back to, I think, AGU 2009, where Katrine Lehmann showed some measurements, and I believe it was Actos, of maybe with the same instrument, I don't know, or an earlier version of.
It was like a fast FSSP.
Oh, was it that? Okay. The indication or my memory from that talk was that you could see shifts in the homogeneity of the mixing as the cloud evolved, and I haven't followed up on that, and I wondered whether that was actually borne out in subsequent papers or analyses. You know, you've shown a couple of snapshots here which show the inhomogeneity of the mixing. I recalled that evolution of the homogeneity as a function of cloud life cycle, and I wondered if you've seen any signs of that.
I know Holger is working, and I've been sort of involved with the work, but I'm not centrally involved in it. They've been looking at homogeneous, inhomogeneous mixing with single particle counting instruments from these clouds in Barbados, where they see the very clear signatures of the subsiding shells. And there they definitely see some hints of a transition from more homogeneous to more inhomogeneous mixing as that shell structure develops, which is perhaps, you know, it's always easy to say it's not a surprise now, but you know, it is a surprise. I think there have been several papers sort of leading up to that hypothesis. Jan and Hermann Gerber and others wrote a paper a few years ago where that idea was put forward, that it could be preconditioned environment making things look inhomogeneous. And so, yeah.
And in fact, if you go to high relative humidity, then the difference really gets smaller and smaller. Am I right? When you get
That's exactly right.
purely saturated
If
air,
it's saturated air,
difference.
then it's just dilution.
Yeah.
Yeah. And so there's no way for us to be able to unambiguously say it's one or the other here, except I would say these points are certainly suggestive of mixing with just higher humidity air.
Just one thing, going back to the instrument, this thing of 3.3 bothers me because you're working on centimeter or millimeter scale, centimeter scales here. Now every 33 meters you take a sample. Have you ever tried to increase that thing and just take 10,000 samples, increase that and see what happens?
We haven't tried, but I don't see a reason that it should
Well, could you then detect
matter,
the
because
transition from the one to the other one, the two graphs that you showed?
that would be great. Yeah, I see what you're getting at. So to be able to have continuous coverage and then to be able to explicitly see when you're getting a transition would be a really exciting thing to do. I would say we're a ways off from that. It's probably more likely that people will be able to do that with a big DNS before they'll ever do it with an airplane. A big turbulent simulation. That's just a good.
Okay, I think.
So if you have a spare $500,000, we'll build exactly the instrument you're asking for. Yeah, I think by the time you get a camera and convince Scott to build some new, where's Scott? He maybe had to leave. Scott, you
Might
need
have to add
build
labor to that, actually.
yeah, to build a new optics and everything. Yeah. It costs a lot of money.
Okay. I think we need to allow it to finish up here. I'm sure we can thank Raymond again.